So the aim of the exercises this week is to have you develop the basic elements in a neural network code, which include the feed-forward stage and the back-propagation stage, where you implement the back-propagation algorithm for calculating and updating gradients, and then obviously the weights and the biases, which are the parameters of the model. Now, the example which we've taken here is an example from electronics, which is a classic case. And the reason why we've taken this example is that the design matrix or the input is very simple. So these are just bits 0 and 1, and it just produces one output. So it means that the output node, there's only one output node. And this is an example which you will encounter in many textbooks. And the reason why we bring it up is that if you're a little bit in doubt about how you set up the design matrix, the weights and the biases as matrices, etc., this is a way which allows you to step through all the stages. And since we don't have that many parameters, it's a very small network, you can actually compare what your code is giving with what you would expect by paper and pencil calculations. So it's an example which allows us to both set up the code, and at the same time, there are not so many parameters, and we can actually check what is going on. So the kind of system here is given by these classic gates in electronics, and the gates have an input x1, so this column should actually be here, and x2, and these are bits 0 and 1. And you have an output depending on the gate, so this will be an OR gate. So in case you have 0 and 0, you get 0, 0, 1, then you get 1, etc. And then you have other gates. And two of these gates, like the OR gate or AND gate, is something you can fit easily with either linear regression or logistic regression, as we discussed in one of the lectures 2 weeks ago. So, talking about logistic regression, in the project, there is actually a subtask with setting up a logistic regression example. Now, you don't need to write a logistic regression code if you have a neural network code. Why? Any ideas about why you don't need to write a logistic regression code? Yeah?
You can just change the...
So, if you have a neural network code, what would you take away? So think of logistic regression. You're feeding in something. There is a sigmoid function which modulates your data, and it spits out something. You can take away backpropagation, and you can take away the hidden layer. So a logistic regression is the same as a neural network without a hidden layer, because the hidden layer adds complications, non-linearities. So if you take away the hidden layer, you actually just have an output node, and that's where you plug in the sigmoid function. And you need obviously to calculate the gradient at the output layer, but that's the same gradient you would calculate if you were to do standard logistic regression. So if you have a functioning neural network code, you don't need to write a logistic regression code. And the thing you would do then would be to compare your neural network without hidden layers with a standard logistic regression code, which comes with, say, scikit-learn. So that makes life a little bit easier, hopefully. Hopefully. So let's go back to this example here, because if you look at the data set which you have, so the data set is given by column x1. So you have 4 lines of data entries, and then you have 2 features. So this is your design matrix. And the outputs are just given by the type of gates you're looking at. It could be an XOR gate, it could be an OR gate or an AND gate. And this would simply be given by these vectors. So this is your data set, which you want to fit. Now, the OR gate and the AND gate can actually be fit with, as we discussed during one of the lectures, with just linear regression. So you could have a line which separates the output. and fit that one. Or you could use logistic regression. The XOR gate, you cannot find a line which separates them unless you want to have a complicated nonlinear object which separates the different outputs. And that's where a neural network actually comes in and allows you to reproduce the properties of an XOR gate. So what we want you to do in this case, and in order to get acquainted with the dimensionalities, is first to set up the design matrix with different inputs and so on. And these are just these matrices here and these vectors. You will set up a neural network with only one hidden layer and two hidden nodes. And then you would set up the output node. There's only one output, and the output can be 0, 1, because this is what you're outputting, just a signal. And we are going to do that with the sigmoid function. That's what's going to modulate the output. You would need to set out the output layer with only one output node and use again the sigmoid function as activation function for the output. And then you initialize weights and biases and perform a feed-forward pass. So I just wanted to discuss the feed-forward pass with you now, and because that's where you would set up the dimensionalities of the problem, and that will define the type of gradients you have to set up. So let's take a look at the system which we have, and I'm going to set up a case here where we are going to now assume, actually I have these numbers, and these numbers, you can think of these numbers as a result of the training. So I have the weights. Actually, the numbers I have here will give the desired output. So we have a perfect match with what we should get. So think of these numbers as the results of a training, but we are going to use them here as the way you would set up the feed-forward pass and the dimensionalities which are needed. So assume now that you have this design matrix X, and then you have a weight matrix for the hidden layer, which contains only two hidden nodes. And then we perform the matrix multiplication, which you would have to do anyway. So if you go back to that case with the images of handwritten numbers, we had something like 2,000 numbers, handwritten numbers, and then each number had 64 pixels. Your design matrix was then something like 2,000 times 64. In this case, it's just a 4x2 matrix. And when you're setting things up, be careful about the dimensionalities, because that's one of the typical errors if we interchange indices. So the design matrix is a 4x2, and the weights is a 2x2 matrix. So when we multiply that out, that gives us a 4x2 matrix, obviously. Then you could think of having a bias vector. So I'm just setting up these numbers, but you could think of having done the training, so you see it. And so you would have 0 and 1. So if you add this one to this one, then what you get then is 0 and minus 1, 1, 0, and these numbers here. So that would be the input to the sigmoid function or any activation functions. Now, in the example here, what kicked in is just my plain laziness. So I didn't want to compute things with a sigmoid function. So I took another activation function, the relo, which is widely used. And this is one of these functions which avoids this dying or exploding gradients, which is sigmoid has a problem with. And this function is just the max value of your entries and 0. So you have a linear relo function, you have rectified options, you have an exponential linear unit, etc., etc. If you look up online, you just search activation functions used in deep learning, you will find tons of possibilities. So they all have the properties that you want them to have bounded, to be bounded. You want them to avoid exploding gradients or vanishing gradients. You want them to be simple. That means that you need few floating point operations to calculate them, and you want their derivatives to be simple. Because the more complicated the function it is, the more floating point operations you will need. And clearly, this is a point, it's a function which you will calculate zillions of times. So having something which is fast is essential. So there are tons of functions, and sometimes you will ask yourself, why is this function used as an activation function? And when you run your neural network codes, your simulations, you will typically play around with different activation functions, because sometimes sigmoid can give vanishing gradients, and then the training will stop. And you may get a mean squared error, which is not the one you want. So if we now go back to the whiteboard here and just look at some of these calculations which we have, and before we look at the final result, let's just set up the network here and switch to the whiteboard. So what we are going to have for this exercise, and if you have a code which does it correctly, you can easily transfer that to the final project which you have. So what we have is an input node, an X1, and then we have this X2 here. So this is the input layer. And X1 and X2 take only values like 1 and 0. We have the hidden layer, so we have a hidden 1, a hidden 2 here, and then these hidden nodes get input from the input layer. So this is modulated by a weight W22. You have a weight W21. And then we have the similar one from X1, which is modulated by W11. And this one is modulated by W12. Now, these guys here, they produce an output, which I'm going to call for A1. And then we have an output here, A2. There is a bias, B2, a parameter we need to fix or adjust by the training. And then there is an output layer, and that produces an output here, which I'm just going to call for A. And this is the same as our Y. And this feeds into the cost function. And into the cost function, you compare that with the target. So this has also bias, which I'm now just going to call for C. It means that this A1 is going to be given by a modulated result via the activation function. So I would have a W11 times X1 plus a W21 times X2 plus a B1. And then I have my A2 here, which is given by sigma of W12 X1 plus a W22 times X2 plus a B2 here. Now, these feed in to the final output. So this output is given by sigma times A1 times W1. So there's a weight here, W1, and a weight here, W2. So the system is pretty simple. So what you have, if you now count, you have 1 parameter, 2, 3, 4, 5, 6, 7, 8, 9 parameters you have to tune in this specific case. So when you have that, you can now compare that in the cost function. So when you do the back, this will be the feed forward stage. And when you do the back propagation, you need to calculate the derivatives with respect to these parameters, starting here, because then you have a cost function. And then you would propagate that backwards. So you can update these coefficients, and then you propagate it backward again, and then you update the coefficients which you have here. And that completes the first iteration. And then you would repeat this till your mean squared error reaches an ideal value, ideally 0. But what you would typically do is to run this through many times, a given number of iterations, let's say 100 or 200 or whatever. And then you would simply stop at that. And if you're satisfied with the results, then you're done. If not, you would run with more iterations. You could have more tests of different activation functions. You can choose the architecture by using more hidden layers, etc., etc. But this is a case where you can actually fit the XOR gate with just one hidden layer and two nodes. So I'm going to show you an example of how that functions. So this is the feed-forward pass, and the reason why I bring it up is that it's so easy to mess up with the dimensionalities of these matrices when you initialize everything and when you do the feed-forward pass. So these dimensionalities, and if you look at the calculations here, what you end up with is something which we call in mathematics an affine transformation, which means that if you look at these operations here, what you're essentially doing is actually a set of matrix-matrix and matrix-vector multiplications, but where the matrices and the vectors are dense. Since we have all nodes in the different layers which are connected. So one way to reduce it, and which is done in a cheap way, is to just include only 50% of the nodes in one, and you would pick them randomly. So at every iteration, you would pick randomly 50% of the nodes. And that means that the dimensionality of the weights and the matrices you're dealing with, the matrix-matrix multiplications are reduced. But this is normally not done that much. So for some of you who are familiar with convolutional neural networks, what we do then is that we reduce the dimensionality of the matrix by filtering. It means that we take away some specific properties of an image. So if you have an image of a house, and that house is given by 200 times 200 pixels, you may reduce that dimensionality by taking away the color of the house, because that's something which you assume is uniform over the whole house. So if you want to recognize houses, you're more interested in windows, corners, doors, etc., and you're not interested in the color. So you can reduce the dimensionality by filtering. So many of these methods, they often have dedicated filters to reduce the dimensionality. But here, we are going to deal with the full matrices. So that's why we call this for affine transformations, in the sense that we just deal with a matrix times matrix with the full dimensionalities. So if we go back to the Jupyter Notebook now, and look at these operations which we started with. So the main reason why I bring these things up is that I want you to think of dimensionalities. And since we are a very heterogeneous group, we have people who may already have finished writing their neural network code, and we have many other people who have never written a neural network code. So I hope this kind of forcing you to think about the dimensionalities helps you getting started with writing your own code. So when you've done these calculations now, you found the activation function or the results of the activation function, which is the ReLO function, where you simply take the maximum value between 0 and what you have here. So clearly this becomes 0 and 0, which we see here. You have 1 and 0, 1 and 0, and 2 and 1. So that's the action of the ReLO function, the activation function. And then what we do next is that we have a output layer where the weights now are set to 1 and -2. So these numbers have been tuned so that the feed-forward pass gives you the wanted output. And in this case, you see now that the output from the output layer, the subscript O here, when you multiply this is a 4x2 matrix times a 2x1 vector, gives you obviously a 4x1, as expected. And you see now that this is the desired output. So pay attention to the dimensionalities. And if you now look at the feed-forward pass and the way you could structure your code, so you would set up the activation function, which in this case is just a sigmoid function. So that's pretty straightforward. And here I'm setting up the input to the specific function. And in the exercise, we're asking you to use the sigmoid function. So what you have here is actually the first pass, the feed-forward pass in this exercise. And you can generalize this. As you will see below, there is a full object-oriented code, which you should feel free to use and look at and use as inspiration if you want to. And in this case, we're just making things a little bit more straightforward and simpler. So you see now that we have the z value, which now feeds into the sigmoid function, and that gives the output from the hidden layer. And this is just a 4x2 matrix, as we saw here. So this is the output which you get. This is the z value, and this is the output you get by the ReLO function. The sigmoid function is different. And then we use that one to compute the input to the output layer. So we have the output from the hidden layer, which we multiply with the output weights, which is actually this operation you see here. And then I put the vector, the bias vector, I put that to 0, but we can actually put that to different 1, if some 0 if we want, so that includes the output bias. And then it produces the probabilities, which are now just given by the inputs to the output layer. And that's the feed-forward pass. So if you run this, and you see now what we've done, we have set up the number of inputs and features, which is the shape of that one. And in principle, I don't need this one because I've already defined it. I just have one output, which I defined by this variable categories. And then I have one hidden neuron. And that's the setup of my network. I define the hidden weights, as you saw in the example above, as the number of features times the number of hidden neurons. So if you have 64 pixels, you have 64 features. So that means that for an image with 64 pixels, you need 64 input nodes. And then the output weights are given by the number of hidden neurons and the categories, which have just one output node. And then you have the output bias, which I just put a random number here, which could be a random number, but here I put it to 0.01, but you can just make this a random number. And then you run it, and then you see that what you get now is something which is not exactly 0 or 1. So you would have to make a choice now. So the prediction which this makes for me, without comparing it to the output, to the target, without looking at the cost function, this is just a feed-forward pass of the network. If I now would put in a threshold here, I could say if this is below 0.5, this is 0. If it's above 0.5, it's 1. So in this case, I'm predicting ones, only ones. So that's not a very impressive result, but this is where the back propagation kicks in. So now you need to calculate the gradients for that specific cost function. You need to back propagate and then update the weights and the biases. So that's the propagation stage. And you have a code example from last week where we went through it, how to set up the back propagation stage. So I'm not putting it in here simply because I want you to think of it. That's where the main thinking has to take place. The feed-forward stage is easy. And the reason why I want you to think about that is that that says a lot about the dimensionalities you have to have set up correctly, okay? Now, one thing you can do is obviously to compare with scikit-learn. And here's an example with scikit-learn for the same case. And what I'm feeding in now, without doing any train test splitting, is just the data. And I have the design matrix. I have the different gates. And now we make a loop over the learning rates and the hyperparameters lambda. So there's something which confuses people when you're dealing with neural networks, because you have so many parameters. So you have the epochs, you have the batches, you may have the parameters in methods like Adam. If you're using momentum, you have a momentum constant, etc., etc. So the data or the parameters to which your results are most sensitive are normally the learning rate, because that depends how your gradients are moving. So how fast you reach the minimum, if you are close to the minimum. And clearly having the learning rate and the hyperparameter, as you saw in project number 1, these are the two parameters which are the most important ones. So if you run with, let's say, between 500 and 1,000 epochs, That is normally sufficient for the gradient descent family of methods if you use stochastic gradient descent. And then you would tune the learning rate and the hyperparameter. And that is what often most practitioners end up doing. In the report, you should actually focus on the optimal parameters. And it means that you would have to run many numerical experiments, and you would run them with different activation functions and also different methods for updating the learning rate. But at the end, what you will most likely see is that Adam is the best method. So many people would just start with Adam and then make a set of calculations with that. And then afterwards, you would test the other ones and see if you just get a better result. And then you would pick the method which gives you the best result. And it could happen that in your setup, root mean square propagation gives a better result. Or even you may see, and I've seen this in scientific articles, people just saying that plain gradient descent did a much better job than stochastic gradient descent. And then we just used plain gradient descent. And we don't understand why, but this is what we got. So in many cases, you have so many parameters that it can be difficult to assess which ones are the most important ones. But overall, it's the learning rate and the hyperparameter lambda. And these are typically the parameters which are tuned when you have fixed a certain number of epochs and batches with stochastic gradient descent. Now, scikit-learn, in this case, we use it with logistic activation function, the sigmoid, and it does by default now use Adam as a method for updating the gradients and the learning rate. So that's a default value, but you can choose other methods. If you run this example here, what you will get is now something which I'm going to display here after all these parameters. And you will see that for a learning rate, this actually corresponds to a learning rate of 10 to the minus 1. This is a case where we have a perfect classification. So only these two cases. So with perfect classification, it means that you're counting the number of correctly classified events and divided by the total number of events. So 1 is the same as 100% hit. So this is the simplest possible way to measure whether your model is doing well or not. Tomorrow during the lectures, we will see other ways of studying a classification problem. So you can set up something which is called a confusion diagram, where you have true, false, false, positive, etc., which is another way of looking at the classification problem. So this is a case now where you find that the learning rate of 10 to the minus 1 is the one which gives you the best result. Now, what I wanted to show you now for the rest of the time here is what follows afterwards, which is an example of an object-oriented neural network code, which contains many of the elements which you need in the project. So if you scroll down this weekly exercise thing, there's actually a code here, which was based on what we have in the lectures, but then Eric and Gregor here, they actually, these are students in robotics, in computer science, and we paid them to do that. So they developed software for CNNs and RNNs and so on. And hopefully this can serve as an inspiration or guide when you're writing your own code. I also put it in here because it serves as an answer to the exercises from last week and the week before on the different gradient methods and optimizers or scheduling algorithms for updating the learning rate. So the first thing you will see is a class which now contains methods like the momentum here. It has adagrad, root mean square propagation, adagrad with momentum, root mean square, and finally Adam. So these are methods. Feel free to look at them because you have probably written your own. And what you could do then is to make a class of it and perhaps copy what you see here, or be inspired by it, because that allows you to structure your code in a better way. I mean, we don't require that you object-orient your code, but it makes it a little bit easier to deal with large numerical projects. So just look at this as an inspiration. And this is just a collection of the functions which we need in the project. So this would be the first part. So that's the part which you see here. So let's just run through it. And this is the way, if you want to test the individual elements, there are specific tests. So if you're using Adam, you would then simply plug in a learning rate. You have now a parameter row, and this parameter row 2, which adds in momentum. And then, sorry, you can then just run through and print out the results here. And then you run over a certain number of epochs. And this is something which provides you the weights after a specific run here. So these are the changes which you have. And there's a list of cost functions. So when you're doing linear regression, then this is the cost for the mean squared error, as simple as it can be. This code does not include the hyperparameter lambda. Just pay attention to that. This is something you need to add to your code. But you find examples of that in the lecture notes from last week and also the lecture notes this week. So in this specific case, what you also have when you are dealing with a regression problem is that the activation function for the output layer is just the output itself. So you don't send it through a sigmoid function or any other function. So if you're fitting a function and you want the output, then the output is just what comes into the output layer. There is no activation function in the output layer for a regression type of problem. That is, you're fitting a function like you did in project number 1. There's another thing I want to have you to think about when you deal with regression and neural networks. So if you think back to project 1, your design matrix contained a polynomial approximation. So you would have a given number of features which corresponded to the polynomial degree which you have. So if you're now dealing with neural network, and hint, universal approximation theorem, would you send in to a neural network a similar design matrix? So what is your feeling? Any good ideas? There's a no here. Vetle? No. Why no? Yeah? Okay.
Because then you're hinting to the neural network that you want that you assume polynomial.
Yeah.
And the good thing of neural networks is that it can take any function, so it will be not that hard to hint that you want to pick the polynomial and pick the best function, which might not be a polynomial.
So this is very important. And the whole thing with the neural network and the universal approximation theorem is that the network should find the best way to represent a function. If you send in a polynomial of a given degree in your design matrix, you are biasing the network to try to reproduce a polynomial, which may not be your data. So just keep that in mind. So that means that when you do the neural networks, you could actually send in a polynomial like you did in project 1, or you just send in the X values, period, and let the network find the best way to express that function. Because if you condition the design matrix, in a way, you're not using the power of a neural network and the universal approximation theorem. So this is something which is important to think of. Now, you will find cost functions like the cross entropy, et cetera, which are used for classification problems. We also have examples here on the whole. Let's just run through this one. There's an example of activation functions. And you will recognize the sigmoid, the softmax for classification problems with more than two classes or two categories. We often use these interchangeably, categories and classes. And then you have a rectified linear unit, the linear rectified linear unit, and there are many, many other ones. So if you have some time, just make a search online, activation functions for deep learning, and you will find a huge list of functions. So these are some of the more popular ones. And what is normally done when we run numerical experiments is that we try different activation functions. And it's common to have the same activation functions for all the hidden layers. You can obviously change activation functions, but it's pretty standard to actually run through with the same activation function throughout. So if you're doing Bayesian machine learning, which is actually a more interesting way, then the activation function is a probability distribution. However, that requires many more floating point operations to produce an output from. So again, if you look at these functions, they are just straight, simple functions. And their derivatives are simple, which means that you don't waste too many cycles on calculating these quantities. And you will see here that we have, for the ReLO and for the linear ReLO, we have actually plugged in the numerical or the actual expressions. And then we have, for the other ones, just the autograd or the automatic differentiation option. Now, keep in mind that if you have a very simple function and the derivative is very simple, it can be useful to hard code it yourself and not use autograd, because autograd introduces an overhead and calls the functions, and that can give you more floating point operations. I think there's a bird somewhere here. Yeah, there's. Or maybe somebody sitting on the roof here and just making that sound. Okay. So this would be the activation functions. And feel free to be inspired, use this. We have the neural network here, I'm just running through it. And then I will just show an example. So this contains both the back propagation part and the feed forward part. There are examples here on specific functions. There are examples of regression cases, how you would use it there. So when you look at the project, you have a regression case. So you could do that for your terrain data or any other function you want to fit. There is an example below here for classification. These are the Wisconsin cancer data. And you can see how you can use that. We have the cost log rate function, activation function sigmoid, etc. So that's the cost function. And then if you scroll down after this multi-class, here we have the XOR gate. So this is the case we've been looking at in the exercises. So you can run the code, which is here for the XOR gate. So you see the number of input nodes is given by the shape of the design matrix, which is 2 here. So we have 2 input nodes, only 1 output node. I set up a logistic regression case, and I set up my output functions to be a sigmoid. My cost function is the log reg here, which actually in this case is the same as the cross entropy. And then I put a learning rate of 10 to the minus 1. And if I run this code, you will now see that it gives me a perfect training. So this is, if you go back to the case we had above with scikit-learn. So I'm using Adam as a scheduler to update the learning rate. If you go back, this was a learning rate of 10 to the minus 1. So if you go back here, you will see now that this number 4 here corresponds to a learning rate in the grid of learning rates, which is 10 to the minus 1. And this is a case where I had the best training. And then, so if you look down here, if I now change the learning rate, if I change this to 10 to the minus 3, for instance, if we do that, then you will get a training accuracy of 50%, which is just like tossing a coin. So this is a pretty poor result, actually. So when you get 50% accuracy, you could just toss a coin, actually. That's how advanced your code is in that case with those options. So these are examples you can play around with, and if you like to use it, feel free to do that. If you just want to use that inspiration, feel free to do that. So we often put in many code examples because we know that it takes time to get at the final code. So coming back to the exercises, if you have a code which does these gates, then that should be a code which can easily be transferred to the data you're going to analyze. So the first thing to think of is the feed-forward pass when you're doing these calculations. And then you could set up manually the way the matrices are multiplied and the way you add the vectors, and just check that your code is doing what it is meant to do. And feel free to use the numbers which you see in the very beginning here. So the simple example which you see on the top here, if we now just go back to the very beginning. So my typical advice when you're writing a code is when after you have initialized and set up the output layers and the input layers and the weights and the biases, then what you would need then is just to perform the feed-forward pass. That is the first step you need. And the code which you see here, down here, does the feed-forward pass, or it gives you an idea of how you should set it up. And the example which you see here shows you how you would define a design matrix. You have your weights. So just make sure that when you multiply matrices and matrices, that the dimensionalities come out correctly. Because this is a 4x2 matrix, which we have here, this one. And the weights is a 2x2 matrix. So that means that when you perform the multiplication, you have to have X times W. And similarly, when you now set up the ReLO function, get the output, make sure that the output has the right dimensionality. And then at the end, when you're performing the final calculation, you have the input, and then you multiply that with the weights, and that should have the right dimensionality of your output, which you then plug into the cost function. So this is something which in the beginning can always, how to say, is a source for errors. So I've interchanged indices so many times that I do not dare to say how many times I've done such stupid errors with I and J being interchanged, and you don't see it before somebody says, and you've been looking at the code for hours, and somebody says, and you just interchange I and J there. It was 3 hours of my life. Okay, so if you have these indices correctly and the dimensionalities correctly in the feed-forward pass, it's very difficult to miss on the dimensionalities in the backpropagation piece. Okay, so I'm going to stop the recording, and then Mia and we are here and to help you guys. And I'm going to stop the recording here. Any questions, by the way? Yeah?
Layers.
Yeah. It doesn't need to be, but because you can have different number of input nodes, yeah, and different number of nodes in the hidden layer. So the matrix W doesn't need to be a square matrix. But yeah. Yeah, that's correct. And you're doing affine transformations, which means that all the nodes from one layer are connected to all the nodes in the other layer. So you're not skipping any of them, but there is no interlayer connection because that would make the training much more difficult in general.